production logs scream error code 57P03. The database is rejecting every new incoming request from your application instances. Open the PostgresQL command line immediately. Execute the command show max connections to identify the current hard limit set on your server. PostgresQL reserves 3 slots by default for superusers. This allows administrators to log in and kill rogue processes even when the limit is reached. Run a query against the PGStat activity view. Count the total number of entries to see how many backends are currently consuming slots. Every connection in PostgresQL spawns a dedicated operating system process. This architecture ensures isolation, but consumes significant memory and central processing unit resources. Each backend process requires roughly 10 megabytes of basic memory. High connection counts quickly lead to memory exhaustion and operating system swapping. Filter your activity query for sessions in the state idle in transaction. These are the primary culprits holding locks and consuming connection slots. Use the function pg-terminate backend with a specific process identifier. This forcefully closes the connection and frees the slot for active traffic. Automate cleanup by selecting all process identifiers where the state has been idle for more than 5 minutes and passing them to termination. Locate the postgresql.conf file to increase max connections. Be aware that this change requires a full restart of the database service. Increasing connections requires more semaphores and shared memory. If the kernel limit for semaphores is too low, the database will fail to start. Adjust the kernel semaphores using sysktl.conf. Set the maximum number of semaphores to accommodate the new connection limit and background workers. Check the ulimit for open files for the Postgres user. Each connection and every open table file counts against this operating system constraint.
The most efficient solution is a connection pooler like PgBouncer. It sits between your application and the database to manage a queue of requests. In session pooling mode, the pooler assigns a database connection for the entire life of the client session. This offers the least throughput benefit. Transaction pooling is the industry standard. It releases the database connection back to the pool as soon as a single transaction completes, maximizing reuse. Statement pooling is the most aggressive mode, but forbids multi-statement transactions. Use this only for simple, atomic updates and read-heavy workloads. Configure your application-side pool using libraries like HikariCP. Set the maximum pool size to a value that balances performance and resource consumption. Enable leak detection properties in your pooler configuration. This logs stack traces of any code that fails to return a connection to the pool. In Java, always use try with resources. This pattern guarantees that the database connection is closed even if an exception occurs during execution. Use context managers in Python with the with statement. This ensures the session is returned to the pool immediately after the block finishes. Set the idle in transaction session timeout parameter in your database configuration. This automatically kills sessions that hang after starting a transaction. Apply a global statement timeout to prevent long-running queries from hogging slots. A 60-second limit is often appropriate for typical web applications. Remember that work memory is allocated per sort or join operation. High connection counts multiplied by large work memory settings lead to system crashes. Transaction pooling can break prepared statements. Ensure your pooler is configured to handle the discard all command, or use server-side prepared statements carefully. Configure transmission control protocol keep alive settings to detect dead clients. This prevents orphaned connections from lingering when an application server crashes unexpectedly. New connections require transport layer security handshakes and authentication. This overhead is substantial, which is why persistent pooled connections are significantly faster. Too many active processes cause the central processing unit to spend more time context switching than executing queries. Optimal performance usually requires fewer connections. Offload read-only traffic to secondary replicas. This reduces the connection burden on the primary writer and allows for much higher aggregate connection limits. Implement advanced poolers like pgcat for sharding and load balancing support. These tools offer better health checking and failover management than older solutions. Monitor the wait event column in PGStat activity. Connections stuck in the extension or lock wait states are often signs of resource contention. High connection churn indicates that your application is not reusing connections. Check your logs for frequent authentication messages and adjust your pool settings. Integrate PostgresQL exporter with Prometheus and Grafana. Set up alerts that trigger when the connection count reaches 80% of the maximum limit. The ideal pool size is often calculated by taking twice the core count of your database server plus the number of effective spindles or disks. Setting max connections to 10,000 without a pooler is a recipe for disaster. The overhead of managing the process table will paralyze the kernel. If using PgBouncer, monitor the Show Pools output. Look specifically at the client waiting column to see if your pool size needs to increase. Auto-scaling application clusters can suddenly overwhelm your database. Always compute the maximum possible connections by multiplying instances by their individual pool sizes.
Implement exponential backoff and jitter in your application code. This prevents a thundering herd problem when the database starts accepting connections again after a surge. Your final checklist includes tuning kernel semaphores, deploying a transaction mode pooler, setting server-side timeouts, and monitoring active session wait events. With these configurations, your PostgresQL environment can handle thousands of concurrent application requests while maintaining low latency and efficient memory usage across the cluster.